In this first lesson, we're going to consider a town in medieval Germany called Königsberg. It was on the river Pregel, and it had 7 bridges to 2 islands, shown here. You can see the bridges 1, 2, 3, 4, 5, 6, 7. The idea was, can a continuous walk be planned so that all bridges are crossed only once? The best way to try this is to just have a go at it yourself. And so let's have a look here. So say we're over on this bank here, and we're going to try and cover all of these bridges and try and cover these bridges only once. We can see I'm in trouble here. I've got to go across this bridge here twice, and so I've started on one bank and ended on the island. Okay, well, we'll try again. Let's start on an island over here, and let's do a figure 8 and see if that helps. Go around here, down around here, across. But I've got the same sort of problem. I'm going to have to go whoop back over this bridge once to be able to get across this other bridge, and I end up over here on the other side. So I haven't been able to solve the problem. The Swiss mathematician Euler had a go at this problem. He first simplified it. He looked at the riverbanks, point B and D, and the points on the island A and C, and he called those dots vertices, sometimes called nodes. He then made the edges in his graph the bridges connecting those points, 2 between A and B, 2 between A and D, and one each between B and C, AC and DC. So we don't call these points dots and lines, they have specific names. So these dots are called vertices in plural or vertex singular. So there are 1, 2, 3, 4 vertices, and the lines are called edges. And the vertices themselves represent the riverbanks and the islands, and the edges represent the bridges. You might recall there were 7 bridges, and you can see here there are 1, 2, 3, 4, 5, 6, 7 edges. Euler discovered the solution to this problem was related to the degree of a vertex, which is the number of edges attached to each vertex. So for this bridge problem, we can see the degree of vertex A is 1, 2, 3, 4, 5, because there are 5 edges connected to it. You can see the way we write this is DEG bracket A bracket equals 5. The degree of vertex B is 3. The degree of vertex C is 1, 2, 3. And the degree of vertex D is 1, 2, 3. So the degree of a vertex could be an even or an odd number. Euler found for this problem there was an odd number of degrees on every vertex, and what that means is the problem cannot be solved or transversed with one single crossing on each edge. Euler in fact proved that graphs with all odd vertices cannot be traced or drawn without lifting the pencil or going over the same edge more than once. So in terms of the Königsberg Bridge problem, it was solved. It couldn't be done. You can't cross every bridge in a single walk without either missing a bridge or crossing one bridge more than once. This new area of maths that he developed was called graph theory, and it's used to analyze friendship networks, scheduling airline flights, designing electrical circuits, planning large-scale building projects, and many more applications. The exercises set for you are shown at the bottom of this page. In this first question, we can see an additional bridge has been added to the problem. Can we actually construct a walk to cross only each bridge once? And can we draw a simplified graph for the situation? Well, if we start here, perhaps, let's see how we go. We could go across this bridge, back onto the same island, back over this bridge, back over this bridge, back over here, and here we are. You can see that we've covered every bridge only once. We haven't started and ended in the same place, but we've certainly covered each bridge once. Why don't you have a go at this? You'll see there's other possibilities. To graph the network, we put in the islands and the banks, and we show the bridges between each vertex. So the degree of A is 1, 2, 3, 4, 5 edges come from A. The degree of B is 1, 2, 3. The degree of C is 4. And the degree of D is 1, 2, 3, 4 as well. Euler discovered for this type of problem that if there are two odd degree vertices, then the problem can be solved. You can cross every bridge only once. But you must start at one of the odd vertices and finish at the other. We started up here at B and we finished at A, but this is in fact two routes. You could reverse it. We could start at A and finish at B. Can you find other ways from A to B or vice versa? Have a go yourself.